All right, I'm here with Nicetu Tibau Vidal. Before we get into your research, let's clarify a few concepts. In physics, we have dynamical laws of motion, such as those of general relativity and those of quantum mechanics, but we also have principles, like the principle of conservation of energy. What's the difference between laws and principles?
All right, that's a great question. Thanks for inviting me. So to answer this question, first of all, we have to say that both are laws of physics. So both are constraints that we have to reality, are constraints that we put to reality. The only difference is in sort of like the hierarchy between these two types of physical laws. So principles are higher in hierarchy in some sense, but also if you're thinking in another way, they are lower. Let me explain myself. They are higher because they are able to provide a more general scope of view of physics. So the restrictions that they put on reality are like not that strong. So you are able to have several dynamical laws for each principle. While on the other hand, dynamical laws are very specific. Basically, they are exactly telling you what the system is doing. They pinpoint exactly the behavior of reality, while principles, for example, the principle of conservation of energy, you can have several dynamical laws that adhere to that. For example, quantum mechanics adheres to that, but also classical mechanics adheres to that, or general relativity. So principles are more general. They provide you also with more intuition of how to find new laws, new dynamical laws. So they guide discoveries. For example, I'm thinking in the discovery of the neutrino, because they found in the experiments that the principle of conservation of energy was being violated. Therefore, some people said this cannot happen. So we propose a new type of particle and it behaves this way. So it guides, like it pushes forward the knowledge in physics, also leading to discoveries of new dynamical laws. So yeah, basically, it's just a distinction that physicists made, but both they are laws of physics. But one, it's like very specific and it has a very strict mathematical formalism, while the others can have different interpretations mathematically or can be formulated differently depending on which dynamical laws you are seeing if the principle holds or not.
Now, you've been applying Einstein's principle of locality to physical systems in your research. So before we get into that, what is Einstein's principle of locality?
Okay. Einstein's principle of locality is one principle that a lot of people believe that quantum mechanics does not hold, but that anybody who does physics or has some intuition of how reality works expects to be true. So it can be broken in two, basically. One, so it has basically two parts. One, it's that basically tells that reality can be divided in systems. So for example, I can say that I have a glass here of water and that this is a chair and that they are different objects and they are not like part of a whole that, okay, they are part of a whole, but they are not, you do not see them, you can see them as independent. But the crucial part is that you understand that the properties of the glass of water or the properties of the chair only depend on the constituent parts of the glass of water. So the properties of the glass of water cannot depend on if the chair is up or down. This would make no sense. So this is the first part, which basically it says world can be divided into subsystems, and the properties of the subsystems only depend on things that are in those subsystems. This is first. Then the second part, which is less controversial, is what everybody more or less when studies like physics in high school or like flying balls or this sort of stuff, it's like also very familiar, which is basically that if I twist something here, if I twist some notch here, this cannot have an instantaneous effect in Mars or here in the US where you, Logan, are. So when you have two subsystems, one can only affect the other if they are touching or if they are really close neighbors. And in this way is, for example, how gravity works or how electricity works. So you have a charge or you have some system, and the way we explain the influence of this system to another, to a separate system, is that there is something in between that mediates this behavior. So this notion that mediators should exist and that things do not happen instantaneously between, that things do not affect each other instantaneously when they are far apart, is the second part of the Einstein's principle of locality, which has to do with how things move, while the first one has to do of how things can be described.
And you've shown that fermions conform to the principle of locality. So what are fermions and why was this a significant achievement?
Okay, I will break this question, I think, into first, I will explain, I'll explain a bit what are fermions, and then I'll explain why I think this is a significant achievement. So fermions are one of the two types of constituent particles in the world, more or less, like in a broad sense. Basically, you can have two types of particles. One that is called fermions and the others that are called bosons. Fermions is one of these two types, and these two types are so-called indistinguishable particles. So let's perform like some sort of recreation of what I mean by indistinguishable particles. So by indistinguishable, what we mean is that if I have two fermions, okay, for example, electrons are fermions, okay, so let's speak about electrons. If I have two electrons, they have the same mass, they have the same charge, they have the same spin, so all the properties are the same, but not only that, they are the same in the sense that you cannot track them, in the sense of if I go to you, Logan, and I place two electrons in front of you, okay, and you say, do perform every measurement you want, like you can do whatever you want, okay, but now you just turn around and I will have the choice of either interchanging them or not, okay? So I can flip both electrons in front of you, and then I allow you to perform, you turn around again, and then allow you to perform any measurement, whatever you want to them, okay? They are indistinguishable because you cannot know if I have performed the flip or not, only by looking at the fermions. Okay. So in this sense, they are indistinguishable, that if you flip them, you do not know if you have flipped them or not. Okay, now let me explain what is the difference between bosons and fermions. So for bosons, what we know is that when I perform this flip, exactly nothing happens. The state of the system is exactly the same under this flip, okay? For fermions, it's not the same. It changes a property, but this is a property that it cannot be measured. This puzzles a lot of people who think about physics, especially in philosophical terms, or what is the interpretation of this. But for fermions, if you flip them, you get an extra -1 sign that every time that you interact with this system, it becomes irrelevant. It doesn't matter if the -1 sign is there or not. So that is why you cannot know if I have performed the flip or not. But the fact is that if I flip them, the -1 sign is there. And everyone expects the -1 sign to be there, but like nobody can detect it under and it's not because we do not have the capabilities of detecting the -1 sign. It's like it cannot be detected. Like mathematically it can be seen. So this is the difference between fermions and bosons, that when you flip them, fermions, you get this -1 sign that you cannot directly measure. So since this -1 sign, it's gathered in the whole system, there is this notion that you cannot know, like you cannot describe this -1 sign only in terms of my left fermion and my right fermion, that you have to talk about this -1 sign as part of the whole. So it was expected that the Einstein's principle of locality it would be more difficult to even put it for fermions. Most physicists still do not know that quantum mechanics adheres to the regular quantum mechanics with qubits, adhere to the Einstein's principle of locality. But even when you talk to them about what if fermions adhere to it or not, they would say to you, oh, but what about this -1 sign? This is completely global, you cannot describe it. So I think it's very significant because we have been able to say, no, you can grasp that and you can make it adhere to the Einstein's principle of locality.
And you did this without using the tools from constructor theory, correct?
Yes.
So why then is it important or useful in solving problems to express the principle of locality in constructor theoretic language?
Sure. First, since the aim of constructor theory is to have a very broad and general framework where you can talk about all the laws of physics, since this is such an important law of physics, like it is almost mandatory to have it in the language of constructor theory. Because if you have a very important law of physics, you want it in constructor theory because it will allow you to do great stuff with constructor theory, because then you can talk about in generality of all systems, regardless of if this specific dynamical law has been followed or not. So this is like the first key point. Like, it's not like you have a choice in constructor theory to either include the principle of locality or not. So, but in this sense also, like you asked why it's important to express the principle of locality. So the question would be, okay, so if you are able to do this without constructor theory, like why do you want constructor theory? The thing is that with constructor theory, you are able to talk about, so with this, I only talked about fermions. What I want is like I want a framework, basically, which I think that constructor theory gives it to me, or it will give it to me, to talk about not only fermions. I want to talk about fermions, I want to talk qubits, I want to talk classical systems, I want to talk bosons, but all at the same time, because I want to draw conclusions about if there exist other physical theories or if not, or what are the real general properties of the structure of reality.